So I'm going to go over this practice with you just to make sure you guys are okay and you understand what it is that you're looking for. So in this very first example here, the first question says, using the pedigree above, identify the genotypes of the following individuals. So we're looking for, in the third generation, individual 3, in the first generation, individual 1, in the second generation, individual 1, and in the second generation, individual 4. Okay, so the first thing we've got to kind of figure out here is what exactly are we looking at in terms of these traits? I may actually jump to the second question here first before we answer the first question, only because one of the first things that I notice is that when I look at this section here, I see that those individuals, none of them are shaded in, which pretty much tells me I'm probably dealing right here where it's not shaded with some dominant trait. I also noticed that in this section here, no one is shaded in, and then the children of 7 and 8 here, none of them are shaded in either. So that's sort of giving it away that they probably all have that dominant trait that has taken over, which is why you don't see whatever this trait is showing up. So I'm going to make the assumption based off of that this is a recessive trait based on the fact that I see these several generations that are unaffected or unshaded, which tells me that the dominant allele must be passing forward. And I'm just kind of keeping that really short and simple for you here. But that's what I've focused on the most, is that I see this whole entire section where there is no shading, so that trait is not visible, which tells me that that's the dominant trait here, not shaded, which means I'm looking at the recessive traits in these 3 individuals. So if I do know that this is a recessive trait, then I already know automatically that these 3 individuals, their genotypes are going to be 2 lowercase letters. So that means, looking here at what I have to label, I actually have to label the person from generation 3, person 3. And so that person there, let's just give it some letters. Let's do lowercase f's. That also means that here, person 1 in generation 1 would also be lowercase f's. Now, person 2 in generation 1, which is the person right here, we have to backtrack and figure out what possible genotype could that person have in order for someone with the recessive trait to produce children that show the dominant trait. So that means it's very likely that this particular parent probably has 2 capital letters, the purebred homozygous dominant trait. That's a possibility. Now, if you try the heterozygous genotype, you know that if you put in a Punnett square, if you do both of them heterozygous, capital F and little f, keep in mind that you also could get this to work where you could end up with all of your children showing the dominant trait, but you would have a 25% chance of them not. So we can actually list the heterozygous phenotype here too, since we don't know for sure which one. And person from generation 2, person 4, if we look at that person is connected to generation 2, person 3. They had children together. What's interesting is both of them do not show the trait, but they have 2 children that do, which means we all know the only way that you have 2 people who have the dominant trait and do not show the recessive trait. The only way that you can have children with the recessive trait is if you somehow have that small chance of creating the recessive genotype. So that means the only way that's possible is if both of these children are individuals right here. Both of these would have to be capital lowercase, right? So in order for them to have children, if you go and you do the Punnett square, both of them being heterozygous, they could potentially produce a 25% chance of having individuals with whatever that original trait was from generation one. Okay? So question 3 says, how do we know for sure that individuals 2, 3, and 2, 4 are heterozygous? Well, I kind of just mentioned that to you before. The only way that you're going to be able to get these two individuals here with the recessive genotype and phenotype is if that recessive allele exists. Remember, we get one allele from mom, one allele from dad. So that means our answer here should have been something along the lines of, we need a recessive allele from parent 1, or from parent 3, and from parent 4. In order for that to happen, genotype needs to be heterozygous. And then our final question on this part, how many children were born to individuals 2, 7, and 2, 8, and what order were they in? So let's find generation 2, person 7, and person 8. And you're going to see that they're connected by this line here, and they have 1, 2, 3 children. So they had 3 children, and their order is male, female, male. And I know this because we put them in birth order from left to right. For this next set of questions, we're looking at a pedigree for something called Huntington's disease. I went ahead and I added a link for you in case you were curious and wanted to know more about Huntington's disease. It is definitely a disease that has been genetically tracked through the use of pedigrees. So the first question says, how many children did individuals 1, 1, and 1, 2 have? And we're going to list them. So right here, these are first generation individuals, 1 and 2. We want to know how many children they had. So all the people connected to them, this person, this person, this person, this one, and this one are all their children. So that means they had 1, 2, 3, 4, 5, 6. So they had 6 children. It says to list them. So we have 2, 2, 3, 4, 6, 7, and 8. That's all of their children. 2, 1 married and had children with 2, 2, and 2, 5 married and had children with 2, 4. Which members of the family are afflicted with Huntington's disease? So, of course, we have a little key here that tells us the shaded means Huntington's disease. So we're going to list the individuals. It looks like 1, 1 is afflicted, 2, 2, 2, 3, 7, and 3, 3 are all afflicted. So every person that's shaded in, you're listing their generation and their individual number. Those are the individuals that are afflicted with Huntington's disease. Now, this next question, let's pay close attention to it. It says there's no carriers for Huntington's disease. You either have it or you don't. So with this in mind, that H there, with this in mind, does that make the disease dominant or recessive? So think about it for a minute. You either have it or you don't. So that means if you're homozygous dominant or heterozygous, you have one trait. If you're homozygous recessive, you have the other. So if there's no carriers, meaning that recessive trait hanging along and can possibly be passed down, that means that it has to be dominant, because if you are homozygous dominant or heterozygous, you've got the disease. If you're recessive, you don't have it. So that's what makes this a dominant disease. Use the disease. So it is a dominant trait because the homozygous dominant and heterozygous genotypes would produce the disease and the recessive would not. Since there's no carriers, that's your key indicator right there, no carrier. So is individual 1-1 male or female? Well, it's a square, and we know that the squares represent males. And then it says what genotype does that individual have to have in order for the children in generation 2 to have the phenotypes that they do. Well, keep in mind when you look at this, these are the parents, afflicted, not afflicted. Notice that they have several children that were not afflicted with Huntington's disease, which means these individuals carry the recessive trait. So let's say we use an H. All these people are lowercase h's. People shaded in orange, they have the dominant trait because we determined that Huntington's disease is a dominant disease. So that means the only way you would end up having some children that would not have the disease and have a full recessive genotype, you would have to have heterozygous genotype here. Because think about it. If you put in this area here a capital H and a capital H, and then a lowercase, all of your children would be afflicted with Huntington's disease. And that's not what happened. So the only way to get that chance of not having Huntington's disease, you would have to have the heterozygous genotype here and the homozygous recessive genotype with parent 2. So that means that parent 1-1 has to be heterozygous. If after completing this you still don't quite understand how to look at some of these pedigrees, I'm going to be giving you some more practice and we will review this. Please make sure you reach out if you're confused so that way I can assist you before you get more confused.